I'm very excited to introduce Mel Andrews. Mel got their PhD in philosophy of science at the University of Cincinnati, is currently a postdoctoral fellow with CITP and also the Natural and Artificial Minds Initiative in the AI Lab, as well as having a super competitive fellowship from the Sloan Foundation to study AI in science. So delighted to hear about Mel's work today. So I'm going to be talking today about algorithmic fairness as a paradigm in AI ethics and whether it's successful as a paradigm in AI ethics. So alternatively, epistemic demands on AI ethics frameworks. I think all of us here today in some capacity are concerned with or are in the business of preventing harm from emerging technologies in one way or another. And I want to make the claim in a more formal manner that this is sort of the essence of AI ethics. I claim that AI ethics is any research agenda or methodology that functions to prevent or remediate harms from AI technologies. I think that's a definition, but I think it's also a minimum viability condition. So if you claim to be an AI ethics framework but fail to meet this desideratum, you're failing as an AI ethics framework. That's my assertion. I'm going to argue today that machine learning fairness, by and large, at least in standard forms of application, has largely failed to meet this kind of minimum viability condition. And I'm going to put it forward as a kind of case study in what can go wrong if we fail to appreciate machine learning itself, AI itself, as a kind of epistemic technology in application, and that there are, in fact, epistemic demands on applied ethical frameworks. So I want to just give a caveat that nowadays when we say AI, a lot of people are thinking about generative AI. I think they're an exciting novelty. I think they might stick around in a handful of applications. I don't think this is the AI that should be of primary concern to us, which is not to say that generative AI can't spark harms, but that the harms that emerge from generative AI are kind of limited by the utility of generative AI, which I think is like radically overblown. So I think we're going to see it fade into the background a lot in years to come. But there's a form of AI or machine learning that is actually really widespread today in what we call socially sensitive applications. This is applications where there's potential for harm to citizens. And it's nearly ubiquitous, and it's going to stick around for a long time. And this is applications of what I'm calling inference-oriented machine learning. So this is machine learning aimed at inference over the real world from real-world data in what are called automated decision-making or automated decision support contexts, ADM or ADS contexts. If we're members of the technologically modern world, we're encountering the decisions made by ADM or ADS systems on a daily basis. These are coming in hiring, these are coming in admissions, in eligibility for social welfare programs, criminal justice, sentencing, hotspot policing, decisions over whether someone belongs in child protective services. There was a big case in Allegheny County, in medicine, in diagnosis, in triage, in determining whether you're at risk for drug addiction when you go to the pharmacy to pick up your prescriptions. They're everywhere, banking and mortgage and loans. And the primary mechanism that is meant to be in place to keep these systems from discriminating, from perpetuating biases, is algorithmic fairness. So what is algorithmic fairness? I'm going to claim that machine learning fairness has been the kind of dominant AI ethics framework in scholarly communities since the deep learning revolution. FACT is in origin primarily a fairness conference. Our conferences, our venues, our discourse surrounding AI ethics in the scholarly community has really circled around fairness to the extent that there's the most extensive body of scholarship, and also, when it comes to applied ML in deployment, I think machine learning fairness has been far and away the most impactful on actual applied ML practices. How does it work? Well, machine learning fairness aims to produce metrics for fairness evaluations, so it's kind of model eval practice. And these are statistical quantifications over a measure of performance of the model compared across demographic groups or sensitive attributes. And it can be used to either detect disparities in how models are functioning across demographic groups, or you can use it as a kind of constraint on optimization to enforce a certain limit of bias in performance across demographic groups. So what is the motivation of doing algorithmic fairness? The precedent historically was fairness through unawareness, it was called, at least retroactively. So this is blinding a model to sensitive attributes. So it can't see your religious affiliation, it can't see your race, it can't see your sex, right? It was found that this kind of blind approach to non-discrimination actually led to perpetuation of harmful biases. Why? Because naturalistic data always contains myriad proxies for sensitive attributes. If you have data about the social world, you can always reconstruct the sensitive attributes of people who are in that data because of just the nature of natural data, the nature of social science data, right? So what problem was FairML looking to solve? I think it was trying to introduce a kind of formal method or decision procedure that could be easily applied at scale, that could be just sort of reflexively applied without doing a lot of critical thinking, without needing to bring in social scientists, without needing to do a lot of complex measurement, without bringing to bear domain expertise, without a lot of laborious effort, right? Your typical kind of software engineer deploying a model at your company could just sort of apply a fairness package and oops, the model's biased, we fixed it, right? It's easily operationalized, it's easily adopted, and there has been widespread adoption, right? Just an example, we know that health conditions, when we don't treat them, can compound, and that health status can deteriorate if you have a lot of untreated chronic conditions. A Massachusetts healthcare system realized it was losing a lot of money on these cases because it didn't treat people up front, and their healthcare their health status deteriorated, their illnesses compounded, and we were spending a ton of money on end-of-life care, right? Past the point when we can actually address the illnesses and cure them. So this Massachusetts healthcare system, this hospital system decided, okay, we should contract this contractor, this software engineering company, healthcare software engineering company, ask them to build a classifier. And the classifier will predict health status, right? Will predict how sick you are so that we can allocate priority healthcare to the sickest patients, thereby saving us money in the long term, because in the long-term time horizon, we're not dumping money onto these patients towards end-of-life care, right? Company builds the model, gives the hospital the model. Oops, it's really racist. The Black and Latino patients have to be like way more sick by objective measures to qualify for the threshold for admittance to this priority treatment thing. Why? Because this hospital system has a history of spending discrepancies across racial categories, right? So in this case, in such a case, we might want to bring in fairness metrics because these fairness metrics can, one, give you a kind of measure of how biased, right, the model is when comparing performance across categories, and because it can be used to sort of enforce a limit on how biased these models can be. So that's some of the motivation of where we might want to apply fairness metrics. To give some nomenclature, Y is a ground truth you're trying to predict, X is covariates, Y hat is our estimate of the label we're trying to predict, and A are our protected attributes like race, sex, religious status, age, things like that, and assuming a binary classification setting, so Boolean valued labels. These are a few of the canonical confusion matrix-based approaches, metrics in algorithmic fairness. There are also calibration-based approaches. There are a lot of different ways of measuring your bias via these frameworks. But importantly, for all outcome-dependent metrics in algorithmic fairness, by outcome-dependent we mean it's sensitive to the base rates in the demographics. It's corresponding to the label you're trying to predict, right? It's trying to match the statistics on the label you're trying to predict. So it's going to be picking up the base rate discrepancies that exist in the data that you're training on, right? Across demographic categories. So outcome independent fairness metric is basically just like statistical parity is a metric that we use in fairness, but importantly, this was not created for machine learning. This is a statistical metric that just says, look at the reference population, match the reference population with the number of people in the predicted label per demographic group that we care about. So it's importantly not specific to ML, not specific to ML fairness, and outcome-independent statistics are not epistemic notions of fairness. It's not an epistemic operationalization of fairness, meaning that it's got a strictly regulatory or normative justification. And when I'm critiquing fairness, I'm not critiquing statistical parity because it's not an epistemic notion and it's not specific to algorithmic fairness as a paradigm. And it doesn't suffer from the epistemic problems that are common in other outcome-dependent notions. So I want to ask, does algorithmic fairness do what it says on the box? Does it work the way it's intended to? And I'm going to claim that it doesn't. What sort of strategy is it? I'm going to claim that it's a metamodeling strategy. And as such, it's a second-order epistemic activity that fails in its stated aims. What do I mean by that? Machine learning, when it's applied in the world, on real-world data for inference over real-world systems that those data are drawn from, is trying to do inference about those real-world systems, right? As such, it's a kind of first-order epistemic activity. In ML, we're training a statistical model algorithmically from data. And I think straightforwardly, this is an epistemic technology aimed at inference. So it's a kind of modeling. I'm going to introduce this category of what I call metamodeling. Metamodeling is now when we have math applied to math to tell you how good your math is at doing the first-order epistemic activity that you've applied it to. So it's a kind of second-order epistemic activity. Basically, it's like I used math to tell me how my math is performing. And I think outcome-dependent metrics, in fairness, are pretty straightforwardly metamodeling activities because they are aiming to tell you if you have discrepancies in performance across labels, across demographic groups, sensitive attributes for prediction on the predicted label, right? So we're trying to prevent harms, right? How is FairML meant to do this?
Sorry, just really quickly. So the first order modeling activity is like the algorithmic model itself. For example, it's predicting, are we going to operate on this patient or not?
Right.
Okay. And then the meta modeling is judging how well that model is performing according to
right. Yeah, so any ML that we're applying in the wild to real world data in order to predict something in order to do prediction or classification is it's trying to do inference about the world in principle, about the kind of ground truth from data that we have from the real world. And then any kind of model eval strategy, and fairness is a subset of model eval, right, is in some sense attempting to tell you how well that first order epistemic activity of machine learning based inference is at doing that epistemic activity, right? But the second order activity, the model eval practice, is also an epistemic activity because there is some truth of the matter, theoretically, of how well the first order model is doing its job. So we want to aim to detect or counteract problematic bias, but what bias do we determine to be problematic? So how should we restrict the scope of FairML? I'm going to claim that the sort of like minimum non-vacuous use for fairness is to detect or prevent bias that is either created by the deploying firm or being amplified by the deploying firm. So at the very least, we ought to not be introducing any new biases. In order to detect that, we need to have some kind of epistemic grasp on the origin of bias in a model. So in order for fairness to be effective, it has to give us some sense of where bias is coming from. And I'm going to claim that it can't actually do that due to a number of confounds that we see in the typical deployment context. So confounds to being able to measure or detect bias with algorithmic fairness tools. The first, and this has been widely noted, is selection bias. I want to say that all of the that's not true. I'm going to say that many of the problems that I'm noting here about algorithmic fairness are problems that scholars in fairness, like machine learning fairness, community members, have themselves noted, in fact, often repeatedly through the years of scholarship that's built up in this paradigm. Many of these problems have been noted. It never leads to a wholesale call to do something that's more epistemically well-founded. And that's what I'm going to say, is that the problems with algorithmic fairness amount to I think, injunction against algorithmic fairness that we should be doing something different, right? So selection bias, okay. You have a selection procedure that the firm, that the classifying entity is deploying that determines whose outcomes are observed. It's a kind of reference class problem. So if the population the model is deployed on differs from the reference class, we have an issue. And a fairness metric will be, of course, blind to this discrepancy. And Callas and Zhu noted that because of this issue, attempting to adjust for fairness perpetuates the same injustices that the policy is infamous for. So adjusting for fairness doesn't actually help in cases of selection bias, right? So let's say you're a software company and you've historically mostly employed men, because at some point in history, like most of the people working in software engineering were guys. The intended target of inference, the label you're trying to predict, is employee quality. And you're trying to do something like draw a statistical association between a resume or whatever applicant data you have and that label, employee performance. But we don't have performance review data for a category of people we haven't employed before. Sure, the applicant pool now in the year 2025 includes a lot more diverse populations than it did 15 years ago. But if we've historically only employed, say, men, we can't find a statistical association between women's resumes and employee review data because we don't have employee review data for women, precisely because we haven't employed them in the past. So you have an issue of selection bias. And as we've said, any attribute we have sort of permeates data, right? If we lived in a world in which you could kind of draw a causal boundary against any variable and there wouldn't be widespread statistical differences in all the other variables associated with an individual, we'd be fine. But that's not the world we live in. Proxy label bias is another form of bias that we see pretty widespread. So a firm deploying a classifier, their measure of the proxy label is biased. A fairness metric is going to be blind to this kind of policy. So like performance review data, something like teacher evaluations are a thing that we know to be biased. So if we're trying to hire teachers, for example, and the label we're trying to predict is teacher quality, and how we've operationalized that is student-teacher evaluations, we know that there is actually a 0.5 standard deviation under rating of female teachers. That's just widely, abundantly documented, that if that's the way you operationalize the label you're trying to predict, you will see a systematic bias, right? Because fairness metrics will try to recapitulate the underlying base rates per demographic category, a fairness metric is going to validate this bias as a kind of fair thing because it's designed to have fidelity to that proxy label, even if it's biased, even if we know it to be biased, right? Another thing that, as far as I know, hasn't been noted in the literature, other than in this one paper we wrote, let's say the firm not only controls the label we're trying to predict, like, do I give you a loan or not, right? But it controls other policies that actually have causal impacts on the outcome. These could, in principle, swamp the outcome, that is the label, in a biased direction, and a fairness metric would be blind to that. So an automated decision support model is helping us determine if an applicant for a small loan in our online banking platform is loan worthy, right? And the label we're trying to predict is loan worthiness, and we have all this historical data on who we've given loans to in the past. Great, we predict a model, we force it to be fair, right, all good, it's fair. However, I as a bank also set the interest rate. And in principle, I could make it such that people from precisely this code and only this zip code are offered interest rates at a rate that they couldn't possibly pay back, whereas these people from the neighboring zip codes get interest rates where they're sort of guaranteed to pay back, right? Like there's a way to kind of causally over-determine the outcome, and I could be radically unfair in how I set the interest rate, or something like bail setting, right? And this, of course, has direct causal impacts on the outcome, like repayment, that I'm interested in, but I could certify the model as fair in spite of this. And then the last thing I want to introduce is the notion of an incoherent proxy, and this is something that, as far as I know, hasn't been noted in the literature as well. That you could choose a proxy label that simply is orthogonal to the thing you're nominally trying to predict. So again, in this hospital setting, we're trying to predict something like illness. And we want to predict illness because we are trying to save money in the long term. Why was that model biased? Well, the proxy they chose to operationalize sickness was hospital expenditure from insurance billing data. Of course, there is an actual base rate discrepancy for that chosen label, but the hospital would certify this bias as correct because, indeed, we did spend very differently on Black and Latino patients from the white patients in the richer neighborhoods. So it would certify this model as being perfectly unbiased, even though we know it to be actually racially problematic, right? We know it to be discriminatory in practice. So there's a kind of like pessimistic conclusion here, which is that, right, fairness metrics could detect bias in some subset of circumstances in which we deploy fairness metrics. They're actually detecting a problematic bias, where they're correcting for a problematic bias. That's certainly the case. We also know empirically, because we've tested benchmark data sets for these types of biases, we know empirically that in the kind of standard deployment setting, there are biases of precisely the sort that render these fairness metrics kind of invalid, right? And we actually know that the degree of biases often in these benchmark data sets renders the fairness metric totally unusable. It's completely unable to tell us anything useful about the underlying model, especially when you have multiple sorts of biases in play at once, which we find is also very prevalent. So there was a paper in which we did causal sensitivity analyses on the presence of these biases in benchmark data sets in FairML. What is more, we can in principle differentiate between a kind of deployment context in which fair machine learning is useful and informative, and a deployment context in which it's unuseful and uninformative, but not with the tools that algorithmic fairness gives us, importantly. It does not give us the epistemic tools to tell us about the first order epistemic activity of applied ML enough to know that we're in a context in which algorithmic fairness would even be a useful thing to do. Algorithmic fairness is only useful when the first order modeling activity of applied ML is actually well posed and we have good data and we know the causal structure of the system at hand and it's kind of canonical causal structure. But of course, in order to be doing that and to know that we're in that kind of favorable epistemic context, we have to effectively do social science. We have to know the causal structure of the system at hand. We have to have kind of canonical causal structure. Sometimes we have to have randomized data. We have to have something like effectively a natural experiment or an experiment. We have to know that the label we're trying to predict is valid. So the problem formulation has to be valid. The operationalizations have to be valid. We have to have high quality measurement practices, and we have to know likely sources of bias. Fairness metrics were introduced in the first place as a kind of decision procedure that was meant to replace the need for doing social science. I think that the use of ML in these socially sensitive contexts and the use of fairness in these socially sensitive contexts are a kind of social science avoidance. It's an attempt at trying to avoid having to do the difficult work of science in a context that I claim demands it. When we deploy automated decision-making or automated decision support systems, applied ML, in these kinds of complex social contexts, so these socially sensitive contexts, we're going to see complexity because social systems are complex. So we're going to see things like interaction effects, cohort effects, selection effects, looping effects, right? Causally circular dynamics, right? And those are the settings where we shouldn't assume that the standard application of ML out of the box is well posed. There's an optimistic conclusion though, and that's that we can do social science. I think a key premise of doing ML fairness, algorithmic fairness, is the idea that the typical firm deploying ADM or ADS systems in the wild cannot be motivated to actually do epistemic due diligence. And I'm going to argue to the contrary that we can actually motivate firms to do epistemic due diligence, and that we really have to. Doing something in the realm of good social science, these socially sensitive contexts, is a precondition for being able to detect bias in any meaningful way. Brute force bias detection methods like statistical parity can give us a kind of like primitive insight into whether there's a problem, but they're not really epistemically sophisticated. And to do something epistemically sophisticated, we have to have the first order application of ML to data be well posed. It has to be epistemically sound. My claim is firms should be independently motivated to address this, because these sorts of foundational epistemic issues like inference misspecification or like catastrophic data quality issues will ultimately, in the long run, hurt the bottom line, because you are building a product that A, doesn't work. You have a product that you think does X, and it doesn't. So in some sense, the product is simply broken. And in another sense, you have no idea what the product is doing, right? If we don't have a well-posed epistemic problem, but we're applying ML to real-world data, in some sense, we have no idea what our model is doing. And that, I'm arguing, is a big problem for anyone deploying ML for inference. For the hospital expenditure case, by selecting insurance billing data as our proxy label that we're trying to employ, that we're operationalizing as a proxy for true health status, we're obligating ourselves to replicate past spending patterns, right? Like if the label we're predicting is expenditure, then we're forcing ourselves in the future to stick to precisely the relevant statistical patterns of expenditure that we've had in the past. But of course, we know that those patterns of expenditure are delinquent. We know that those patterns of expenditure are defective. They're not doing what we want them to do because we're spending too much money. So precisely in operationalizing sickness in this incoherent way as hospital expenditure, we're hurting the bottom line. We're doing precisely the thing we want not to do, right? A parallel case, a real estate management platform in recent years had been deploying a thing that predicts how likely, what quantity of money a house is likely to go for. It predicts the cost of a house, right? And it was doing so in order to give users an estimate of how much to sell or buy a house for. But this platform wasn't using that in order to actually intervene on the market and buy up houses. At some point they said, oh, we have this great predictor. We have, like, it must be the world's best machine learning prediction of the housing market. We should go buy up a bunch of houses. Without realizing that, of course, now you're doing social science, right? Now you need a social scientist. Now you need an econometrician. Now you need someone who's an expert in housing markets. Because, of course, there are all these sorts of causal dynamics that you're ignoring here. And they lost billions, right? This company basically went under for a time because they thought they were predicting X and they were predicting Y. And if you don't care to specify the inference problem at hand, you will hurt yourself, you will fail. In some percentage of cases, you will fail because you don't know what you're doing. And I think it's really important, not just if we care about harms flowing from the use of machine learning in the wild, but if we actually care about the bottom line, that we figure out what good epistemic practice is, and we find ways to motivate or enforce that. So the claim is, if we want to prevent or remediate harms from ML, we have to figure out epistemic best practices for applied ML. These are going to be domain specific, right? These are specific to context of application. These will always require domain expertise brought on board, right? And we need to figure out how best to promote those best practices that will often involve bringing to bear human domain experts in contexts of application, right? In developing and deploying these models. The even bigger takeaway is that applied ethical frameworks, like AI ethics, like algorithmic fairness, have duties to be epistemically responsive to the context in which they're supposedly applied. You have to have some sort of empirical grasp on the subject matter, in this case, machine learning, right? And how it's deployed, in what context it's used, what are the dynamics in play there, right? You can't just do normative theorizing in an applied ethical setting with normative theoretical content. You need to have empirical content. You need to know what you're applying an applied ethical framework to. Or the normative theorizing is garbage. It's useless because it's not actually, it's pseudo applied. It's not actually applied to the thing you're theoretically applying it to.
So in a sense, you said that to have these models perform properly, do the first order epistemic task, we need social science. Isn't it a bit circular, since when we do social science, we also have these machine learning models that we use to then derive the claims that then will support these other machine learning models? Like, I use machine learning models to develop theory in social science setting. And wouldn't I have already a problem there of how do I think about fairness when I'm building the social science that will then power the machine learning models that will then be deployed down the line?
I think it has to be a back and forth always, right? So yes, it's kind of circular, but it's not circular in the sense of being viciously circular in the logical sense, right? It's circular in the sense that yes, it has to be a loop where the social scientists talk to the statisticians, talk to the machine learners, talk to the social scientists, consult the prior literature, speak to an econometrician, etc., right? Like circular in the sense that it has to be an open dialogue, and to do each part of it, we have to keep the other experts in the loop.
Thank you.
That's basically my conclusion. This is the end. But I do want to thank some collaborators, Nick Fishman, Jake Fox, Andrew Smart, Stephen Fall, Abiba Berhain, Zach Lipton are all collaborators on this, and I've had some support over the last couple of years working on this.
Thank you for the talk. So if I understand correctly, it seems that the high-level takeaway is that when you're deploying machine learning models in practice, you need to take into account subject matter expertise and think seriously about the actual dynamics at play of the problem that you're trying to work with, and the condition of the data that came before. This seems, maybe I wish it was obvious, but also it's great that you're grounding it. But also, you said during your talk that we should have an injunction against this form of fairness, metrics, method of doing things. And to me, that seems a little disconnected. It seems that the takeaway that I have from your talk is that this is not a sufficient condition for guaranteeing fairness in practice. But it could still very well be the case that it's a very important condition or building block to getting fair outcomes.
Yeah, I think using something like statistical parity is a good first approximation of it. It can sometimes tell you that something is wrong. But then for the application of outcome-dependent fairness metrics, to tell us something informative about the performance of the model, we would have to basically have done good epistemic work in the first place. And if we've done the good epistemic work in the first place, my claim is doing algorithmic fairness is kind of redundant then.
I don't know if I agree with that. So take, for example, I know you only briefly mentioned it, but like the work on like multi-calibration, right? So my model is multi-calibrated if across a large set of groups which I pre-specify, the probability that my outcome is what I say it is exactly the probability that my model gives, right? Now, you're right that this can perpetuate prior bias in the data, and so you can't use it out of the box for any sort of problem. But if I have a well-specified problem that I've thought through carefully, like, you know, what is the likelihood that a patient has this particular side effect, given like these medical attributes, then this could still be a very useful and important measure, and making a model which is multi-calibrated after, as you said, doing the first order epistemic work is value added.
I think in some contexts, but I think it's not the typical use case. Like, I think the typical use case of fair ML and the typical use case of machine learning in general in these socially sensitive contexts is not one that is well posed enough to make fairness evaluation non-arbitrary. And I think the way that fairness has historically been framed is also implicitly telling us that epistemic performance, so in this case like accuracy, right, is intrinsically opposed to normative quality like fairness. And in effect, quite the opposite is true, right? Because we treat fairness as a constraint on optimization, these are treated as opposed, when in fact, in reality, fairness and epistemic sufficiency go hand in hand.
Yeah, we can talk more later.
Really great talk, Mel. I really like how clearly and authoritatively you made the argument for why machine learning should be grounded in social science. I'm very curious about how you've brought these findings to practitioners, especially practitioners in industry, and what their reactions have been. To me, because I'm trained as a social scientist, I'm yeah, this makes sense. But I'm curious what machine learning practitioners in industry who implement these fair ML toolkits think, and how they react to your arguments.
Yeah, I think the basic reaction is, oh well, how will we motivate that? And I think there does need to be the thing is, I don't think it needs to be re-incentivization. I think companies need to be retrained in understanding their own incentivization. And some of that is taking into account long-term profit horizons in addition to near-term profit horizons, making a tool that works is actually better for the bottom line in the long run. But I think incentivization and some even institutional organization will have to change for this to become an actuality.
Yeah, I mean, I think the idea that building a good product is good for the bottom line is sort of, I mean, you would think that's true, but that's not necessarily true, right? A lot of startups have venture capital backing, and they come with they want to build a good product, but on the way to building it, it's all about well, we have to launch the product, monetize it, and then we forget to do the social science, we forget to do validation, And I would argue that it's not always, I mean, you know, I went to all these like HR AI conferences and people like openly say like, oh, all the data is biased, but companies want these models, so we're building it. So like everyone knows, it's not like the practitioners don't know, but they still think they have a valuable model that can be monetized. So like I think the incentives, I wish it was be that easy, that we can just say like, well, don't you want to build good models? So like listen to this. I don't think that's actually kind of the reality, unfortunately.
Yeah, I think the mass healthcare system example is a really good example because the paper on this was by Ziad Obermeyer and colleagues, and what Obermeyer et al. Did was they detected the bias in the model, and then they said, okay, this label doesn't make sense. Can we at least take the expenditure and correct it by something as silly as like just objective number of chronic illnesses, of serious chronic illnesses, and by just correcting it by a factor of some actual objective measure of health status, they were able to build a model that just worked to do the effectively. I mean, it was not perfect, but it was both better at doing the thing the hospital wanted in the first place, which was a cost-saving measure, and significantly less biased against the Black population of patients, right? And I think when you bring domain expertise on board, the solutions like that are like win-win solutions are just abundantly clear in most cases. There's some percentage of cases where you're trying to predict something that's just you can't predict it, and then bringing the expertise on board, it says you're trying to build a magic 8-ball. Mm-hmm. You might think you want that, you probably don't want that. You may as well use an actual magic 8-ball for that, right? But I think the majority of cases are cases where there can be a win-win solution, and we just have to kind of motivate that and find those people.
So, correct me if I'm wrong, but like one of the takeaway, as you also mentioned, was like you want to have domain experts who then lay the epistemic foundation, like identify causal relations, other variables. If you're like in practice, how do you know when to stop? Like, because like there can be multiple variables like you might not even know about, right? How do you find all of that and then decide afterwards, after you've got all the groundwork done, then in practice do the algorithmic fairness? Like at a certain point, like how do you go through that threshold and then do the fairness work?
Yeah, well, you can't include everything that's like causally salient. For instance, you have to make difficult decisions. At the end of the day, social science is hard, and there's a lot that is always going to be epistemically unavailable to us. We right. A lot of stuff we literally can't observe, even if we have access to an experimental population, right? Or right, like even if we can look at the counterfactuals, even if we have a ton of time, et cetera, there's a lot we can't know. But within those bounds, there are best practices we can employ, and those are often going to be, this is a terrible cop-out answer, but those are often going to be case by case. What is the appropriate level of granularity? But the good news is that like people have been doing like social science for a long time, so there are precedents for most of the cases that we're interested in deploying machine learning. We don't have to reinvent the wheel. We're often inclined to in machine learning reinvent the wheel, but we don't have to. There's often a literature on precisely the thing we're trying to do. And we can employ expertise, we can consult that literature, we can consult the experts.
Thank you. I was curious about your restriction of your argument to fairness criteria that are like outcome dependent or in some way epistemic. I was curious if there's a way that like epistemic deficiencies can apply also to normative evaluations. So something like selection bias making it impossible to figure out if the 4/5 rule is being violated because you don't have enough applicants from a certain subgroup to like even confidently estimate like the if there's parity in selection. Yeah, and then more generally, like what or how do you think you would draw the limitations of what kinds of criteria your argument could or couldn't apply to?
Yeah, I feel like the outcome independent metrics, like statistical parity, are so primitive, they're so brute force, that usually when we're deploying them, we have some sense of awareness of how primitive they are, and what their epistemic limitations are, which is that they're I mean, it really is just like match the reference class with respect to A. And I think it's almost less of a hazard than the outcome dependent metrics, because I feel like people are less aware of how primitive the outcome dependent metrics are.
I have a very basic question. At one point you had the model with binary fairness predictions, and I'm curious, maybe because I'm not as familiar with the ML fairness space, like to what degree is part of the problem trying to create this binary classification of this is fair and this is not fair? And how much can you have like, we are becoming more fair, and especially grounded in like this, like I don't really believe we have good data for what a fair system in any of these contexts looks like. So how do we get someone closer to that?
Yeah, so quickly, the binary classification setting refers to the label that we're trying to predict. So that's not a property of the fairness metric, but a property of the first order model we're applying. So we're just talking about like a setting where we're determining if someone is loan-worthy and the labels are loan-worthy or unloan-worthy. But in terms of the second part of your question was more about,
I guess maybe fundamentally, how do you do the meta modeling? And what does the meta modeling, can it really tell you if something is fair or not when we're, like how do we know what is fair?
Yeah, at the end of the day, there's so many decisions to be made about what kind of bias we're trying to either not introduce or correct for, and those are ultimately like normative considerations. At the end of the day, if we're restricting ourselves to not building a model that perpetuates a certain kind of historically ingrained lack of access to resources that might create successive levels in which like women are not given access to STEM education, and therefore the top graduates of CS programs are not predominantly women. It's right, like there's so many levels at which we could go back and ask what bias is admissible here. And ultimately, I mean, like one thing we do is appeal to the law, and what it tells us is allowable kinds of bias to admit into this kind of decision procedure. There's been a number of legal scholars in connection to the algorithmic fairness literature have made many arguments that pertain to how legal doctrines surrounding discrimination ought to be applied in algorithmic fairness cases. And that's, of course, one source of like normative consideration here that's useful. Did you have it?
Yeah, but if we're at time, I can ask it after, or it does now.
Are we at I have no idea.
We're pretty at time.
Past time?
Yeah.